Okay, let's not get too.
Okay, guys.
I know I am a legend.
13.4. We are going to be doing more complex fractions, just a few more, and then we're going to be looking at using trigonometry now to solve for unknown sides. Okay? So our first example is x plus y all over at 2x to the negative 1 plus 2y to the negative 1. So what we notice here is that we have a couple variables with negative exponents. The negative exponent is only attached to that variable. If it was attached to the whole thing, it would be in parentheses, right? So what we need to do then is we need to get rid of those negative exponents first. Do you guys remember how to get rid of a negative exponent? Take it to the bottom or take it to the top. Now, this is actually a 2x to the negative 1 over 1. So because these two variables are attached by addition, we can't just move them up to the top. We actually have to move them down to the denominator of the place that it's already in. So that's going to give us x plus y over 2 over x plus 2 over y. So that's all we have to do. So you do have to take care of them individually because they are attached to each other by addition. So we can't just move them up to the top. The only time we were able to do that was when everything was multiplication. So now this looks like exactly what we just did several minutes ago. So what would be the least common multiple here? xy. So multiply every single term by xy. In the numerator, nothing is going to cancel because our x plus y didn't have fractions at all. So that's going to just multiply to x squared y plus x y squared. All over. In the denominator, the x's are going to cancel, so that's going to leave us with 2y plus the y's cancel, 2x. This looks way too complicated to actually be done, right? So look at it and see if we can factor anything. Okay, so GCF. So what's the GCF in the numerator? XY. So just pull out the XY, and that leaves us with x plus y all over, what about the denominator? 2, and that leaves us with y plus x. Is x plus y the exact same thing as y plus x? Yes, because in addition order doesn't matter. So the whole thing comes out to xy all over 2.
So addition order matters, doesn't matter, but subtraction matters?
Correct.
Okay.
Because if you think about it, 2 plus 4 is 6, and 4 plus 2 is 6.
Okay.
But if you're subtracting them, it doesn't come out the same. So example 2, x to the negative third plus 27 to the negative 1 all over x squared minus 9. Same thing. Because both of these negative exponents are attached by addition, we can't just move them to the big denominator. So we're going to make 2 separate fractions in the numerator. So that's going to be 1 over x to the third plus 1 over 27, because we're moving the whole thing, so the 1 stays on top, all over x squared minus 9. Don't factor that yet. Okay? So what would I multiply this time to get rid of the denominators? 27x to the third. So multiply everything by 27x to the third, 27x to the third. And this x squared minus 9 is all one term, so leave it all together, 27x to the third. Okay, don't distribute that one. And I'll show you why, because it's going to make things a lot easier for us. So the x cubes are going to cancel, so on top we're going to be left with 27, right? Plus x cubed all over. Now, I didn't distribute the 27x cubed because this was already a difference of 2 squares. So if I distributed the 27x cubed, that would throw off my difference of 2 squares. So I just left it on the outside. So we're going to multiply the 27x cubed, and then let's factor that difference of 2 squares. X plus 3 times x minus 3. Technically, this is exactly the same as if I had distributed it, because when I factored, I would have ended up taking the GCF out in the beginning anyway, okay? The reason why this is a little bit more ideal is because this is now a sum of 2 cubes. It's 3 cubed plus x cubed. So let's factor that. We have a small parentheses and a large parentheses. Same, opposite, always positive. So in my numerator, guys, what do I put in the small parentheses? 3 plus x. What about the first and the last term? 3 squared x squared, so that's going to be 9x squared. And what do I put in the middle? 3x. All over 27x cubed times x plus 3 times x minus 3. Do you see why I wanted you to leave everything split up? Yes, why? Because the x plus 3's are going to reduce. Nothing else is going to reduce because this is always as reduced as possible, or as factored as possible. So let's just rewrite it as 9 minus 3x plus x squared all over 27x cubed times x minus 3. You won't be able to do any more than that. Okay? Okay, guys, example 3. 6y to the negative 1 minus 3x to the negative 1, y to the negative 1, all over 3y to the negative 1 plus 3x to the negative 1. My negative exponents are only attached to the variables, so those coefficients get to stay in the numerators. So when you took care of those negative exponents on your own, you should have gotten 6 over y minus 3 over x and y both go down, so xy, all over 3 over y plus 3 over x. So the negative exponents were only attached to the variable, so those numbers stay in their numerators, okay? What would my lowest common denominator be? xy. So let's multiply everything by xy because we need to get rid of all those fractions. So multiply every single term by xy using what property? Which one? Distributive. This is distributive property. Okay. Okay, so we multiplied everything by xy. Here is what you should have got. The y's cancel, so we're left with 6 times x. xy totally cancel, so minus 3. Y's cancel here, so that's 3x. And the x's cancel, so that gives us a plus 3y. Everybody good? Okay, any GCFs that we can pull out? 3 in both, right? So that's going to be 2x minus 1 all over 3 times x plus y. What do I get to do with those 3's? Reduce them. So what does our answer end up being? 2x minus 1 over x plus y. Can I reduce the x's?
No.
No, they're attached by addition and subtraction, so you cannot reduce them. You must leave them the way they are. Okay? Last one, and then we're done. Last trig problem. Here's what I'm going to do. I'm going to give you a trig identity. That's really blurry. And then I'm going to give you a blank triangle. So I am telling you that in my triangle, the tangent of A is 4 over 5. I want you to find the cosine of A. Okay? So the tangent of A is 4 over 5. Find the cosine of A. Here's the triangle. All blank, except for I tell you where A is.
I get it. Got it.
Okay? So your triangle is totally blank, except I tell you where A is. So let's look at what we know. Tangent is what over what? Opposite over adjacent. And do I give you a fraction for the tangent? Yeah, 4 over 5. So plug that in to your triangle. The opposite leg of angle A is 4, and the adjacent one is 5. So the opposite leg is 4, and the adjacent one is 5. I am missing the hypotenuse. How can I find the hypotenuse? Pythagorean theorem. So let's do it really quick. A squared plus B squared equals C squared. So that is 4 squared plus 5 squared equals C squared. 16 plus 25 equals C squared. 16 plus 25 gives us 41. And when I take the square root of both of those, we get C equals root 41, and that's a prime number. So our hypotenuse is root 41. Okay, so the question now is, find the cosine of A. Go. Okay, the cosine is adjacent over hypotenuse. The leg that was adjacent to angle A was 5. And the hypotenuse we found was root 41. We cannot have a root in the denominator, so we have to rationalize. 5 times root 41 gave me 5 root 41. Root 41 times root 41, just 41. So that would be your cosine. Okay?